Hey everyone, ready to dive into the world of engineering? Let's get started. In today's video, we're diving into the fascinating world of PCB manufacturing, a crucial process that underpins nearly all electronic devices we use daily. From smartphones to medical equipment, printed circuit boards or PCBs are the backbone of modern technology. We'll explore the various stages of PCB manufacturing, including design, fabrication, and assembly, while highlighting the significance of each step. Understanding PCB manufacturing is essential not just for engineers, but for anyone interested in how technology works. So, whether you're a tech enthusiast or a professional in the field, stick around as we unravel the complexities of PCBs and their vital role in our digital age. Materials used in PCB manufacturing. When it comes to PCB production, the choice of materials is crucial for performance and reliability. One of the most common substrates is FR4, a fiberglass reinforced epoxy laminate known for its excellent electrical insulation and thermal stability. Another important substrate is polyamide, which offers flexibility and high temperature resistance, making it ideal for specialized applications. Conductive materials, particularly copper, play a vital role in creating the pathways for electrical signals. Additionally, the solder mask is essential for protecting the copper traces and preventing short circuits, while the silkscreen layer provides important labeling and design features. Together, these materials ensure that PCBs function effectively in various electronic devices. Designing the PCB layout. Designing a PCB layout begins with schematic capture, translating circuit diagrams into a manufacturing-ready format. This step ensures all components are correctly represented and connected. Following schematic capture, designers must adhere to design rules and constraints, such as trace width and spacing, to ensure reliable board functionality. Popular KD tools like Eagle and Altium Designer streamline this process by helping visualize and optimize the layout. Mastering these tools and principles is key to creating efficient PCBs for various applications. Printing the PCB. Printing a PCB design onto the substrate involves photolithography, a method that transfers intricate designs with high precision. The process starts by applying a photoresist material to the substrate, which is sensitive to UV light. The PCB design is then projected onto the substrate using UV light, hardening the exposed photoresist. The unexposed areas are washed away, revealing underlying substrate. Precision is critical, as even minor inaccuracies can lead to faulty connections or performance issues. By maintaining meticulous attention to detail, manufacturers produce high-quality PCBs that meet strict performance standards. Etching the PCB. Etching is essential for removing unwanted copper, creating precise circuit pathways. Typically, this involves a chemical etching process where the board is submerged in a solution that dissolves exposed copper, leaving the desired circuit design. This step is crucial for functionality and reliability. To address environmental concerns, some manufacturers use laser etching, which reduces chemical waste and offers greater precision, promoting a more sustainable and efficient PCB production process. Drilling and plating. Drilling and plating are vital for creating vias and pads on a PCB, facilitating component placement and electrical connections. Precision drilling ensures components fit correctly and function as intended. After drilling, plating enhances conductivity by depositing a thin metal layer, usually copper, into the drilled holes. This improves electrical performance and strengthens mechanical connections. Understanding the types of vias, through hole, blind, and buried, is crucial for designing efficient electronic circuits. Solder mask application. Applying solder mask protects the PCB from environmental factors and prevents electrical shorts. Types of solder masks include epoxy and liquid photoimageable LPI masks, offering durability and ease of application. The process involves screen printing, applying the solder mask material over the PCB while leaving exposed areas for component pads and traces. The solder mask acts as a barrier against moisture, dust, and contaminants, reducing the risk of shorts and enhancing PCB reliability. Final assembly and testing. The final assembly involves precise component placement and soldering, ensuring each part is securely attached and correctly oriented. This process can be manual or automated, followed by soldering techniques like wave or reflow soldering. Rigorous testing, including automated optical inspection, AOI, verifies PCB functionality and reliability. Testing helps identify defects or issues that could affect performance, ensuring PCBs meet quality standards for their intended applications. In this video, we explored the intricate PCB manufacturing process, from material selection and design to etching, drilling, and final assembly. Each step is crucial for the functionality and reliability of electronic devices. Key takeaways include the importance of precision in design and manufacturing, the role of solder masks in preventing shorts, and the necessity of thorough testing to guarantee quality. Understanding these processes is essential for anyone interested in electronics. That's all for today. Stay tuned to Tech Blueprint for more clear and practical engineering content.